This is an example of a chi-square goodness of fit test. So the first thing we notice is the chi-square formula here. We're going to have a summation of this term. And we see another formula here, the expected frequency. That's the probability times the sample size. But we'll look at these formulas in more detail in a couple of minutes here. So let's start with the question. A developmental psychologist would like to determine whether infants display any color preferences. A stimulus consisting of 4 color patches, red, green, blue, yellow, is projected onto the ceiling above a crib. Infants are placed in the crib one at a time, and the psychologist records how much time each infant spends looking at each of the 4 colors. The color that receives the most attention during a 100-second test period is identified as the preferred color for that infant. The preferred colors for a sample of 80 infants are shown in the table below. Do the data indicate any significant preferences among the 4 colors? Test with alpha equals 0.05. So the first thing to notice is that this is one of those no preference type situations. So here, the null hypothesis is that the infants wouldn't have any preferences in colors. So you should see an equal distribution of proportion of infants within every color. So 100% divided by 4 is 25%. So we do have a sample of 80 infants, and so that's something that we got to keep track of. But let's actually start solving this problem. The first thing we got to do is state the null and alternative hypothesis. So the null, and we're going to represent it here with boxes representing all the categories. So we have the categories for those 4 colors, and we're saying is that there should be 25% here, 25% here, 25% here, 25% here. So there should be no preferences in colors amongst infants. Our alternative hypothesis is that at least one is different. So the second thing we're going to do, and I'm going to do it down here, is draw just a visual, a sketch, something to kind of help you provide some intuition as to what we're doing. So we're gonna we have to identify the cutoff region here, and so for that we need the alpha level, which is 0.05, and we also need the degrees of freedom. And so degrees of freedom, that is actually the number of categories minus 1. So we have 4 categories here, so that's 4 minus 1 equals 3. So now we can actually grab our chi-square probability table, and across the top row we can identify the 0.05 alpha level, and our degrees of freedom was 3, so we have a cutoff of 7.81. So the degrees of freedom again on this table is the leftmost column, and we do have 7.81 as our cutoff. So when we finish calculating our statistic, we should have a greater value than this if we want to be able to reject the null hypothesis. So now that we have our cutoff, let's actually go ahead and begin calculating. But before we actually start plugging into these calculations, we need to know the values of our expected frequencies. So for that, we're going to use this formula that the expected frequency is a probability times the number of people within that group. So, or the sample size, I mean, which is 80. So for these sorts of problems with no preferences, all of these are going to be the same. So we just have to do the calculation once. So we have that the expected frequency is the probability times the sample size. So we get probability of 25, 0.25 for a fourth, 25% of sample size is 80. So really we're looking at a fourth of 80. So a half of 80 is 40 and a half of that is 20. So we're looking at 20. Okay, so then our expected frequency is 20 within each category. Okay, so now that we have our expected frequencies and our observed frequencies, we can start plugging them into this formula. So this formula, the summation notation, is just simply explaining that we're going to iterate and add terms to the summation based off of these instructions here. So for instance, you know what, I'll just actually write it out. So the first term of the summation would be, and I'm going to write it down here under the 3, it would be the F observed of the first group minus the F expected of the first group all over the expected frequency of the first group. So you can see here, this just says 1, so that's the first term of the summation. And similarly, the second term of the summation, you know, this ticker, the I equals 1, moves to 2. So then we just replace all of those i's with 2's. And so what we're looking at is we're going to do, oh, and that's a squared, by the way. So we're going to do the observed frequency of the second category minus the expected frequency of the second category, and that's squared over the expected frequency of the second category. And for our final term, we're just going to get the observed frequency of the third category minus the expected frequency of the third category over the expected frequency of the third category. So the summation notation is just telling you to go through that process for each category, each group. And in symbols, it looks like this. But from our table, we're really just going to be going, if we're looking at the columns, each column is, you know, the first category. So we're going to do this first column and go through that this procedure, and then go through the second column, and then the third column, and so on. And that's what the notation means. And you can use, visually, you can use this table to kind of help you kind of view it that way. That's why I set up the table this way. But let's just go ahead and start plugging in some of these numbers. Once we do this, we have our statistic, and we can compare it to our cutoff value. So I'm just going to fill in these sections that I know are going to be the same for all of the terms. And I'm just going to start plugging things in. So for the first category, we're looking at 25 minus 20. And that's over the expected frequency of 20. So all of these are going to have an expected frequency of 20. And that's ... And I only did 3 of the terms here, and so I added ... to symbolize that it keeps going. But I'll add the other one here on the side. So all of them are going to have a denominator of 20 because that's the expected outcome for each category. So the second term, we're looking at 18 minus 20 over 20. Then for the third one, we're looking at 23 minus 20 over 20. And for the fourth one, 14 minus 20 over 20. 14 minus 20 over 20. So I'm going to make the numbers pretty small down here. Hopefully you'll still be able to see it, but hopefully everything will fit. So 25 minus 20, that's 5 squared, that's 25 over 20, plus 18 minus 20, that's 2, negative 2, square that, that's 4 over 20. And add another term. 23 minus 20 is 3, square that is 9, so we have 9 over 20. Then we have 14 minus 20 is negative 6. Square that is 36 over 20. So we can see here that we have a bunch of terms over 20. And so we have, that's 40, that's 65, 74. 74 over 20. So let me just punch that into my calculator. We have 74 over 20. That's 3.7. So 3.7 is our final number. And we can see here that it doesn't reach our rejection area. So we're over here somewhere. And that means that our final decision has to be to set it aside here. So we're going to fail to reject the null hypothesis. So basically interpreting this means that there really are no preferences amongst colors and the way that babies view them, the way that infants view them. So yeah, we just have to, we didn't find evidence against the null hypothesis. So as it stands, there are no preferences.